Hello everyone, and welcome to the AI Research Roundup. I'm your host Alex, and today we're diving into some fascinating work in the AI space. We'll be looking at a paper titled VLM-R1, a stable and generalizable R1 style large vision language model. The core idea here is inspired by recent success in using reinforcement learning, specifically a method called R1, to boost reasoning in large language models. This paper explores extending that same R1 style reinforcement learning, but to vision language models, aiming to enhance their visual reasoning capabilities using rule-based rewards. Okay, so figure 1 here actually gives a really nice visual overview of this whole VLM-R1 pipeline. On the left, you see the base model. It's asked a reasoning question about which item might short-circuit the laptop, and, well, it gets it wrong, highlighting the pen holder. Then, in the middle, that's the VLM-R1 framework itself, showing the data preparation, the VLM module, and the core reinforcement learning loop using GRPO, where the model tries different answers, gets rewards, and updates itself. Finally, on the right, you see the result. The RL model, after training, correctly identifies the red mug as the potential hazard, showing improved reasoning. Okay, so building on that high-level overview, Figure 2 here gives us a more detailed flowchart of the VLM-R1 framework itself. It breaks down that reinforcement learning loop we saw into more specific steps, like defining the custom reward function, preparing the specific training data, and defining the VLM module. Then it shows the actual training process: model initialization, confirming parameters, generating multiple candidate sequences, calculating rewards for those sequences, distinguishing good from bad, and finally computing the GRPO loss to update the model. It also highlights the framework's flexibility, showing support for various VLMs, custom datasets, and different tuning approaches like LoRa. So we've seen the overall framework and how it works. Now, Figure 4 gives us a practical example related to one of the specific tasks they focused on, which is referring expression comprehension, or REC. This figure really illustrates the difference between the kind of data used for training, like RefCoco, shown on the left, and the more challenging out-of-domain data used for testing generalization, like Lisa grounding on the right. The training example, identifying, quote, the lady with the blue shirt, relies mostly on appearance or location. But the testing example, finding the soccer goalkeeper, needs the model to use, well, world knowledge to understand the role before it can locate the person. It's a good visual for the increased reasoning demand. So moving from the REC task we just discussed, this next figure drills down into the specifics for the other major task they tackled, Open Vocabulary Detection, or OVD. It shows the exact problem template they use. You can see how the model is instructed to find a list of target objects, and crucially, how it needs to output the bounding box coordinates in a strict JSON format. It even specifies what to do if no objects are found. And below that, well, it shows the format for the thinking prompt, requiring the model to explicitly output its reasoning process within those think tags before giving the final answer. Okay, so we just saw how the model needs to format its output for the Open Vocabulary Detection task. Now, Table 2 here actually shows us some concrete results comparing the performance of the reinforcement learning approach versus standard supervised fine-tuning. This specific table focuses on the OVD task using the two-filtered evaluation dataset, comparing the 3 billion parameter models. We can see metrics like mean average precision, or MAP, greedy precision, and greedy recall. And, well, the takeaway is pretty clear. The RL model achieves a higher MAP at 21.1 compared to 18.5 for the SFT model, and shows really significant gains in precision and recall too. It really demonstrates that the RL training is boosting performance on this detection task. Okay, so those were some strong results for RL on the detection task. Now, Figure 5 here shifts back to the referring expression comprehension task, specifically looking at performance on out-of-domain data. This graph compares the RL model in green against the SFT model in orange, plotting their accuracy on the Lisa grounding dataset over training steps. You can clearly see the RL model's accuracy climb substantially higher, reaching over 63%, while the SFT model's performance kinda stagnates or even drops a bit. It really highlights how the RL approach significantly boosts generalization compared to SFT when faced with unfamiliar data. So that graph we just saw showed the trend visually. And well, this table actually provides the specific numbers behind that referring expression comprehension comparison. It compares SFT and RL accuracy across different training steps on several datasets. You can see on the in-domain RefCoco sets, RL performs well, often slightly better than SFT as training progresses. But the really striking difference is on the bottom row, the LISA grounding, out-of-domain data. Here, the RL model's advantage grows consistently, reaching 63.14 accuracy at 600 steps, which is over 8 points higher than the SFT model. It really quantifies that generalization boost we saw in the graph. So yeah, those numbers really drive home the point about generalization we saw visually. Overall, this VLM-R1 paper demonstrates that reinforcement learning is a really powerful tool for training these large vision language models. It clearly boosts performance on complex tasks like detection and grounding, especially improving how well the models generalize to new situations. And well, that kind of robust generalization is critical for making AI truly useful out in the real world. That's our roundup for today. Thanks for listening. I'm Alex.